Hello there. A few weeks ago, I talked about this question 953, verifying a alien dictionary, which is that we've been given the ordering of the characters for some alien language, and also a list of the words that is supposed to be sorted based on that ordering, and we want to verify that. So looking at the example, we have hello and Leetcode. We just compare the characters in these two words, in the adjacent two words. Location by location, we find the first difference, which is H and L. Since that hello comes before Leetcode, we kind of want to verify that H it's coming before L, and according to the ordering, it's indeed the case. So it's fine that these list of words are sorted based on this ordering. So it's given the ordering and the list of words, we want to do this verification. So it's relatively simple. The question I want to talk about today is called it's 269 Alien Dictionary. It's kind of the opposite of that. So we've been given the list of words that are supposedly to be sorted based on some unknown ordering of the characters in a language, and we want to derive that, deduce the ordering. So some quick notes before we look into the detail about the examples is that there might be multiple valid ordering of the letters, so we can return any one of them, it's fine. So it's basically that what I'm guessing is that the code correctness checking system here is just going to take the ordering that your function return and the word list of words being given to you, and just directly call the solution from 953. If that passes, you're fine. That's for this. So when there can be multiple valid orderings, just a quick example is that if we have something like AC and AB, we can derive that C has to come before B in the ordering in this alien language, but that does not say anything about A. So we can actually just insert A in all the possible locations here. You know, ACB or CBA or even CAB. All these three should be fine, because all we need to know, all we need for the list with these two words to be sorted is that the C has to come before B. If that's the case, the ordering, the location of A doesn't really matter. So that's what the numbers, the notes here says. The other note is that if there is no valid ordering to satisfy to make sure that the words being sorted in the list, then we can return an empty string indicating that there is no valid ordering. A quick example is that z x z. So when we compare z and x, we find that z has to come before x. But when we compare x and z, the second pair, we find that the z has to come after x. So it's immediately we have a contradiction there. So that's indicating that there is no possible ordering for this case to work. So let's look at the example 1. It's a little bit more generous, so we can use that to get some more insight about this question, what this question is really about. So let's look at that example. So this is now input. So we compare this word by word and try to kind of deduce the orderings. When we compare a WRT and WRF, what we can find is that T has to come before F. When we compare the second pair, WRF and ER, we can determine that W has to come before E. When we compare ER and ETT, what we can see is that R has to come before T. And when we compare the very last pair, ETT and RFTT, we can see that the E has to come before R. So that gives us the pairwise kind of ordering. All we need to do is to rearrange this in a line. So it's kind of like it should be W to E, E to R, and R to T, T to F. So it's a linear sequence, strictly linear sequence of ordering of this five nodes. So 5 characters, but also nodes if you treat this like a linked list or a graph, a directed graph. So the characters become nodes, and we basically derive a path of traversal in the graph, if you will. So this is the ordering WERTF, which is the answer here. So for this question, we actually only have one valid ordering. It has to be this. Any kind of adjustment to the orderings here will cause this list of words to be the relative ordering to be violated. So so we now see it's pretty much a graph traversal, graph question. The technical term, I guess, for this question is called the topological sort. I'm not sure if you learned this in CS fundamental courses, but even if you don't, you kind of say that for this particular question, this particular one, we want to start the traversal with W. We can, if you just kind of rotating it, it will become a tree. The W is like the root node here. The reason that W is the root node is that it has no incoming links. So we just scan through this few graph here, and we find the nodes with no incoming edge. It has to be the root, so we start from there, and either we do BFS or DFS. We're gonna traverse the graph with the ordering WERTF. It doesn't matter whether you choose BFS or DFS in this simple example here, but we just traverse to one traverse, and we can get the ordering. So that's that tells us that we want to do traverse in the graph to come up with the ordering. So let me actually just write a little bit more complex the example, because this is kind of like a degraded version of graph. It's more like a single linked list. So I'm gonna create some more complexity in there, so that we might be able to compare the difference between BFS and DFS in solving this problem. Just by the way, both of those can work just fine. So let's say that we have a graph that kind of like split it in 3 ways in the very first kind of level position. I'm just randomly throw some characters in there. Maybe an M. Maybe a Q here, and back to M. So let me use arrows to indicating the edge here. How am I gonna deal with that? This? Yeah, good enough, close enough. Anyway, here's just a slightly more complicated graph that let's say that we kind of derived based on the sorted words here in the list. Whenever we do a comparison, like a T and F, we draw an edge between those characters, and we come up with something like this, a little bit more complicated. But we can arrange them by the direction of the in order the edges, to put the source node towards the left and the target node towards the right, and topologically it looks like a kind of like a level to level. If you just compare this, T and O are in the same level, R is slightly later, S is even further. Q is sort of is sandwiched in between O and M. If you compare the vertical level kind of thing, if you want to think reasoning about the BFS, but for DFS it's quite obvious. You just follow the links and you traverse towards the right. The deeper the depths, it's more towards the right in this graph here. So if we do DFS search, what kind of ordering that we want to do, when you think about the binary tree traversal, the post order, pre-order, in order, of course there is no, I don't think in order makes any sense here. Just compare pre-order and post-order. We actually want to do post-order traversal. So let's say that we start with W, we choose to go R and S, in the DFS kind of fashion. Once we process the S, reach the S, there's nothing happening afterwards. We do a post ordering of S, and then backtracking to R, we can do R, add the R to the ordering. So let me just put it in here, S, R. Once we processed R, we back to W, but W still have stuff we should visit. We find T. Since that the stuff that T points to, R and S, are already been processed, we can do a post ordering of T here. And then back to W. W still have work in the bottom here, so we go to O, M. So M has nothing there, so we can put M here. Back to O, O to Q. The only stuff that Q have pointing to has already been processed, so we put Q here and O and back to W. So that way we derive the kind of like the reverse ordering of the ordering of the characters. So topological orderings, if you know the technical term for this order. So if we do DFS, we are gonna end up with the reversed order if we do post-order traversal on this graph, post-order DFS traversal on this graph. Also we can do BFS. When we look at the nodes here, W is going to be on the first level. So the first level is going to be W. The second level is going to be the nodes that just one link away from W. It's going to be R, T, and O. Note that we can directly put T onto the T and O onto the ordering. Those are fine because it only has one in order incoming links from W. If we pretty much process all the nodes that comes before it. In the case that in the kind of DFS search, when we process W, we decrement the in order, incoming edges to T and O by one, and then we can know that there are no nodes that should come before T or O, so we can put them onto the ordering here. But for R, it's not the case because R has two incoming edges. Once we process the W, there are still one more nodes that need to be processed before R in order to make us we are be able to put R onto the ordering. So once we process the T, we can actually put R there. So we will come up with some kind of ordering like Q and M here. That's the ordering we're gonna derive if we do BFS search on this graph. So both are valid. Let me try to reverse this to do a comparison, I guess. W, O, Q, M, T, R, S. So it looks, yeah, both are fine. It's just for DFS, it's WOQM and WTRS. It's more like it's the DFS version, but for the second ordering, it's WOTR SQM. It's more like the level-wise BFS search results, but both are the valid results. So we can do either DFS or BFS. the good thing about BFS is that you have this incoming links kind of like criterion for help us to determine whether we should put the node onto the ordering. If there are loops, which can be, because the case here zxz tells us there could be loops. So when we look at the graph here, z and x, we process the x, we decrement, we find that actually the we couldn't even find a starting node to process this graph in the BFS kind of fashion, because every node has exactly one incoming link. So we're not going to be able to find the route to start the traversal. So that's obviously not a good sign for this question in the very beginning. So what if we have something like this here? Z, am I blocking? Oh, no. Okay. So z to x, and there are a cycle here, x to y. So when we process the z, we decrement the in edges to x. So it's decreased from 2 to 1. Then we still couldn't put this on the ordering, and since that we process pretty much everything towards this left, and this thing has a in order that's larger than 0. That's not 0, meaning that there must be a cycle. So we can pretty much terminate early on. So based on the the in degrees for every vertices in the graph, if we do BFS search, we can actually terminate early on based on we can automatically terminate early on. The ordering are not going to be filled up because there's no chance we're going to put X onto the ordering if there is cycle here. So in the end, we just look at the length of the ordering that we generated compared to the vocabulary size, and we can know whether we finish the BFS search on the graph or not. But for DFS, we have to have explicit code to handling the cycles. So for that reason, I'm gonna code up the BFS search code first and then do the DFS. So just a little bit of summary here. BFS is gonna, for BFS we want the adjacency list and in degrees. We're gonna decrement the in degrees for nodes. When it reaches 0, means we process all the nodes before it. So at that time we can be safely to put that node onto the ordering. So we can and if we do DFS, the only thing that we need is adjacency list. So we do this post order. So it's going to be something like for next node in adj list of this particular node, we're gonna call the DFS function. So after we process all the nodes that's done after that in the ordering, then we can put the pushback. We can put this the node onto the ordering. So that's kind of the post order kind of a ordering. Then we just reverse the ordering to get the final result. One note is that we need to have code in DFS to handle cycle. So that's pretty much the few lines summary of the difference between BFS and DFS. It's required inputs and how the main logic in there. So yeah, let's code up the BFS version first. So first thing first is to construct the graph. So we'll end up with the in degrees of the nodes and the adjacency list. So I'm gonna just look up in my notes here so that I don't spend a lot of time writing mistakes. So this is to convert the character, get the unique characters for each words, and then do a union to reduce that to the total unique nodes, characters in this vocabulary. So that's coming up with the total vocabulary there. Vocabulary being the it's the alphabets, total alphabets for this language here. It's getting that from this line here. Then we initialize this hash map to store the alt edges, which is the from node to nodes, and we're gonna populate this in the in a for loop afterwards. And then is the in degrees, which is int here. Every node has a 0 in degree incoming edges in the beginning. And we're gonna have a array to store the ordering, list to store the ordering, which is initially to be empty. So the graph processing here is for the pair of words. We're gonna check the character by character in the corresponding aligned locations in the word. If we find them to be equal, we just continue. Otherwise, we will. That's indicating there is a difference, so that we can form the edge between the two nodes. So let's. If they are equal, we can continue. Otherwise, we would do C2 will have an incoming edge from C1, so we just increment the in degrees for C2, and they're going to be the out edge from C1 to C2. So that's the populating the adjacency list and the in degrees statistics. When we handle the first inequality there, we pretty much can be done, because compare the stuff afterwards doesn't make any sense. If we haven't break throughout the for loop, we want to actually compare the lengths of these two words. So that's to handle the case when we have something like ABC and AB. If that's in the ordering is totally wrong, because ABC has to come after AB in whatever ordering. So just to catch that, we can put an else statement here. So this is a little bit, when we're doing the graph processing part, we can already terminate if we find the case like ABC to AB in the word list. So it can potentially save a lot of unnecessary traversal afterwards if the graph is not valid to begin with. So to do BFS, we're going to use a queue. So what's gonna be on the queue in the beginning is the nodes like W, which has no incoming links. So we get that by taking a difference between nodes and the keys in the integrace, which is the nodes that has no integrate. That's exactly what the nodes like W are. They has to be towards the right left in the ordering. So that's now our starting point. Okay, is the DFS search. We just pop a node from the queue, and we can add that to the ordering. So that's pretty much that. We added app W to the ordering. Then we want append TOR to the queue. So when we add the node to the queue, we want to decrement their in degrees, because we pretty much use the edge there. So we can decrement the in degrees. And if the node has no, the in degrees become 0, we can actually put them onto the queue. So this requirement checks prevents the cycles being leaked into the be getting into the traversal. So otherwise we will end up with I guess kind of like a infinity looping here. So this guards in that, and since that we don't put the cycle into the queue. Onto the queue, we actually save a lot of time if that's actually happened. So this is a DFS search. Nothing special. Popping off a node, add that to the ordering, and decrement the degree, because we actually utilized the edge, so we can decrement the degree for the next node. When we actually processed all the nodes that's before this next node, that's indicated by that that node's in degree drop to 0. We can put the next node onto the queue, so that the next time it pops out, it will be added to the ordering. So in the end, we just return the ordering in the string format, and that's when there's no cycle. So if there are cycle, the ordering gonna be only including those nodes that's not in the cycle. So it's gonna be short. Because the nodes that involved in the cycle are not going to be put onto the queue based on this criteria. So if cycle exists, the length of the ordering is going to be smaller than the number of total nodes. So this is the code for this DFS solution. Let me quickly check. Looks okay. Nope. Oh, okay. So I shouldn't return false. I should return there's exactly one case here, A, B, C, and A, B, exactly like the one that I thought about. Okay, so in that case, we should return the empty ordering, so it's an empty string there. Makes sense. So let's submit this one. Yeah, it's working. Just relatively quite slow, and so that's DFS. Let's code up modify this into a DFS solution. So for DFS, we don't need the integrates. Let's just quickly summarize, go over the summarization here again. we're gonna process the node, traversal the nodes in DFS fashion in a postal order kind of manner. So we do DFS first. After we processed all the nodes that after the current node, we then put the node onto the order. So as a result, it's in the reversed order. So in the end, we have to return the order reversed. And there will be code to handle the cycles in there. The graph processing part is the same, except that we can drop off the integrate processing there. Because we no longer need that, but the adjacency list is the same. Then we're going to use a hash map to keep track of the nodes being that we have visited. And the fact it's a hash map, it's indicating that whether the node will cause a cycle or not. So let's just quickly note here. So the DFS function is going to be just taking a node, and if node is we have already visited it, we're gonna let me actually code put the main logic here first, and then deal with the detail about the DFS. So we're gonna do this. Well, we still have nodes. We want to explore in the DFS kind of fashion. We'll pop it off, pop a node off the I think I will use a set here. Is it a set? Yeah, it's a set union. Oh yeah, it's a set. I'm gonna call this DFS function, and it will populate the orderings. It will put the node onto the orderings inside the function, but this DFS should return whether it has detected a cycle or not, so that we can actually terminate it early on if we indeed find a cycle there. If we has a cycle, we're going to return an empty string early stopping. Otherwise, we're gonna pretty much remove the nodes from visited from nodes, and take a difference between nodes and visited, so that pretty much it means that we have done DFS search in this portion. Then we can remove all the nodes in there from the total number of nodes that we want to explore. And in the end, we just return the string representation of the ordering, which is reversed. So then it's the detail for DFS. If the nodes is visited, we can just return the because we want to grab whether it has cycle or not. We look into the hash map to return the node. Otherwise, we would just before we go further into the graph, we are not going to be able to tell whether this node is will cause a cycle. So the way to determine it is basically, if we do DFS, we find T and go to R and go to S, and if S has a link to T, which we already processed in this particular DFS call, then we know that there is a cycle. So we can check the hash map to find out whether we have a cycle or not. So in the beginning, we just put the node in there and say, as far as we know so far, there's not going to be any kind of cycle caused by this node. We go about to explore deeper. When we really find a cycle, we will definitely mark this to be true later on. So for the nodes that's after this particular node, the next node after the node, we're going to recursively call DFS to explore that part. if there is cycle there, we'll just call, it's the same story for the node here. We know that the front node will definitely lead to a cycle, so we mark this visited node to be true. Actually, we can just return true here to terminate even earlier. So once we processed all the nodes in the graph that's towards the right for this given node here, let's say W, if we process all the nodes there, that's the final time we push the node onto the ordering. So that's the post order here. And if it can succeed after, there's no breaking intermediate here, then we know that this node will not cause a cycle. So yeah, actually I made a mistake here. It should be true in the beginning. We assume that you will cause cycle, but if we can successfully explore the graph in a DFS fashion without finding a cycle, then we can declare that it's being verified that there is no cycle there. So yeah, I should think about this a little bit more carefully when I talk about this early on. So we just return this. So how do we modify this since that in this case we also return that, how do we modify this to be a little bit more concrete, compact? Can I just do this? But this will cause everything to be indented by 1. I don't like the look of that, but I think it should be equivalent to the previous code there. So if it's in there, we don't even trigger this part, we just directly return that. Otherwise, we will try to populate it first, then return that. So it should be the same. Okay, so so this is pretty much the DFS code. Do we have arrows? This is graph processing. All we dropped out is the in-degree processing. Everything else is the same. So when we process the graph in DFS version, we use this visited hash map to keep track of whether the nodes will cause cycle or not, and also whether it's being visited in the DFS search or not in doing the search there. We just, for the nodes that we haven't started DFS search yet, we're gonna grab a node there and initiate the DFS search. If we have cycle, we terminate early. Otherwise, we mark all those nodes we visited in the DFS search to be visited and remove them from the nodes that we want to explore. So that in next iteration of this while loop, we end up with a smaller target to search. This is slightly inefficient because if we populate this visited by 2 consecutive DFS searches, if we do the difference, it doesn't matter because this it's gonna be upper bounded by the number of characters in the vocabulary, which is likely to be constant. So the time here is okay. Yeah, so I think the code should work. Let's just run it. Oh, I hard-coded this example there because when I was early testing it. Okay. I guess I should try to submit this. It's a slightly faster. So I guess go back to the time and space analysis. The graph processing here, the worst case is the total number of characters in here. So let's say that we have the strings to be the words to be pretty much all share the same prefix, very long prefix. It was just the one last letters being different across the board. Then we pretty much are gonna examine all the number of characters in the proportional to all the number of characters in the input. So that's just the order of total characters in the input. That's for time, and for space, it's the nodes here are the alphabet size. The out edges is upper bounded by the square of the nodes. If we have in the crazy case, we have all the pairwise nodes there, so it's the alphabet squared. The in degree edges is obviously alphabet size again. For the graph traversal part is it's the number of edge plus number of nodes in both DFS and BFS. So that's some very crude analysis of time and space. I don't think you can go better than this. I think DFS is definitely going to be a little bit more space efficient. Not necessarily, because we have this hash map here, which is pretty much just doing the job for the in degrees. So BFS, it's a pre-order. You come up with a pre-order, so that's why you don't reverse that. But for DFS, it's a post-order. In BFS, you use the in degrees to make sure that you processed all the nodes that have an order smaller than you before we append that character onto the ordering. So it's pre-order, but for DFS it's post-order. We process all the nodes after us. Then once those nodes are taken care of, we put ourselves onto the ordering. So yeah, the visit here is doing the same job as in degree to a certain extent in two aspects. One is to determine when we can put a node onto the ordering. The other thing is to detect cycles. So that's the two solutions. I know it's been a little bit rough when I talk through this. I definitely like this question. I think it's the level of difficulty is even it's hard. It's even if you don't know topological sort, you might still be able to work through the graph processing part and at least partially finish the DFS or BFS. If I'm interviewing, I think I will go with the BFS because it's you pretty much just syncing from left to right, and you have things taken care of before you actually put this onto the ordering. So you don't have to do reverse. So the reasoning, I think, it's a little bit more streamlined. All right, so that's pretty much it. Yeah.